Okay, so let's do a case in which we might be interested in putting a spring constant on there. I'm not going to be too concerned about the geometry, so I'm just going to make any old geometry will do. So we'll just make that geometry for lack of anything better. So it could be thought of as a beam. We'll go in, we'll pick plane stress, nothing fancy there. We'll go to the boundary mode. We'll select them all, Control A, double click, and double click again. I'll make them all free surfaces in that they're essentially they're gnomon and they have no surface force on them. But I need to fix one in, so I'll fix that one. I guess I'll need to load one in, so I'll load that one with a -1. I'll go ahead and take my standard that he gives me. E is 1,000 and 0.3. I'll just keep that. But I'm going to look at the right end here. And if you stare at this, let's see. Wait a minute. Oh, sorry. Go to there. Okay, now I'm going to a mixed. Now it's kind of hard to see that, but let's write all this stuff down. If there is, yes, there is a marker. So if you write all this stuff down, let's make a comparison. Here's what I'll do. So I'll click each one of these. First one, I'm going to do the gnomon. Okay, so I don't know if you can see it too well, but it basically says here, NC, gradient of U, plus Q, U, and I believe that's equal to G. So I have to kind of be careful there. Now he's got some spring constants here which didn't play any role yet. But if you look at this, okay, think about it like this. And I think I'm going to put a different surface. I think I'm going to put a little extra part up here to the side. Okay, let me do that because I want it to be on an object here. So hang on. I'm going to go back and put a little spot right here on it. And I'll just have it sticking off the side. Go to the boundary mode. Now I'll select them all. Double click them. Make them all free. Come back. Make this kind of cantilevered there. And then I'm going to worry about this bottom part. Okay, so if I look at this, and this is, now I'm looking at this condition, I see, oh, I didn't load the top yet, did I? Let's load the top. Okay, so I'm going to load the top with a -1. Okay, now that I've got that, I'm going to take a look at the bottom. Well, here, I'll tell you what let's do. Let's go ahead first, mesh it, run it, plot it, and deform the mesh. So if I deform the mesh, kind of looks like, so all I did is did a beam where I loaded across this top surface right there. I got this little part that's just sitting there that the reason I'm going to mess with it is I'm going to mess with that bottom surface and essentially put a spring on the bottom surface here. So there's a couple ways I could do that. Let's run backwards to this thing. I'll close that and go all the way back to the boundaries. I believe I should still have everything set. There's my minus. Let's go to this bottom one. Okay, so if I go to this bottom one, the first thing is he has a matrix that sits here and looks like that. He's got this G1 and G2. You can see on the right-hand side of that. But let's sort of take a look at this Q matrix, which actually the Q, in our case, would be, I'll sort of go in here and do it like this, plus U1 and U2. I'll sort of hold off on this one. I'll say, what do you say, normal dotted. It really should be dotted. And really, technically, it should be C times U in here. And so, what this ends up being, plus, this ends up being the applied load. In other words, if you think about it, PL over AE is equal to delta, but AE over L times delta is equal to P. In essence, this part becomes AE, and what it turns out to be something like that. Del over L ends up being this derivative. So this, from the equation, this becomes the loads. But you can have a spring here. He calls them Q11, Q12, Q21, and Q22. And then you need your G's, which will have G1 and G2. Let's get rid of that. So ordinarily, you don't have anything here. So this becomes the load in the X direction, and this becomes the load in the Y. So let's start monkeying with this. And I'll leave this one's 0, and that one's 0, and I'll make this a number. And let's see what happens. So I don't know, what's a good spring constant? How about 1, for lack of a better? Now, what we'll see is I'm going to increase that spring constant more and more and more and more. Okay, should be able to. So nothing really, didn't notice much. Now I'm going to go back in here and go, how about that for a number? So you notice what kind of happened. So, and I can't really tell, but, okay, I can if I draw it down to the bottom of the screen, though. So if I line that up, so I'm touching this part with the bottom bar here to try to find out, did this little part reflect at all? So I don't know, because here's how I can, well, no, I can't really find out, because before I deflected it, where was the bottom part at? Let me do it like this. Okay, so if I touch that to the bottom, so this is the undeformed shape, right? So if it didn't deform at all, here, this part would stay at that level, right? And so if I run it again, did it deform? And yeah, it deformed a little bit. Okay, so it slid down, it still deformed a little bit, it went down. Now let's do this, okay? This sounds weird. I'm going to run back. I'm going to go in here. I'm going to put in 1e to the 20 and be quite ridiculous. Run it again. Well, now that's, okay, that's right. He scales all these. So in effect, I can't figure out what that, I'll have to dump it out, and maybe there's a way to, let's see. If I deform the mesh, user entry, I don't want to do a user entry. How about arrows? They're scaled proportional. Let's take a look at that. So in essence, these are the deflections. And so what you notice is the deflection of this bottom slides mostly to the right and down just a small amount. Whereas the beam here, this one remained fixed and it deflected down. So the deflection of the bottom would look kind of like that. So in fact, the bottom of this didn't deflect that much at all. If you go back to it, oops, I just lost my boundary conditions, didn't I? Or did I? Nope, they're still there. If I go back and put in there like a 2, run it, you'll see it deflected.
So in other words, this little edge deflected down a little bit. So what essentially that boundary condition does, that Q22, is a spring that basically sits vertically and essentially retards the motion that gives. It's like putting that bar on. Does that make sense?
I could do this as well. This is a little bit odd, but there's a lot of things odd in this world. Let's say I wanted to put 1e to the minus 20 here. And then you run it. You'll notice, I don't know that you can tell that much. But essentially what happened there is there's a spring
in that direction, keeping the thing from sliding to the right, left.
Oh, well, let's see. Oh, does it? Hang on. Okay, let me get rid of my arrows. I'll still look at deformed, though. Okay, so you're saying... Okay, well, I guess I goofed it up, too, because I went in and did this. Oh, I see what you're saying. So, in other words, you see the stress here. Is this what you're seeing? And then you go back, and then I'll make this like a 2 or something. So instead of that large number, I'll make it a 2. Yeah, and it doesn't have any stress on it. So, yeah, that's actually a good. I should have done that, but yeah, all the stress gets moved back over into here. So essentially, you know, this is a kind of a way to supply a boundary condition that way. Here's what's weird. Okay, let's do something like this. Let's see. If I'm deflecting, okay, think about this. You got to think about this. If I'm deflecting
in the U, I want to push a spring in this place.
Okay, let's try something. It may not make good sense first. So let's do this. That doesn't make good sense. But what you've done is for every unit you move down, you shoved it that way. But it's kind of hard to determine what stress that would be. You know, how would you do that? That doesn't make any physical sense. So why would you think, here, let me do it like this. Why would you think there's a matrix like that here? A 2 by 2.
Why is there a 2 by 2? Any idea? Because I can go in and make these numbers anything I want. But a 0, 0, 0, a very large number. So in other words, when it deflects downward, I'm supplying force in the x. So if it goes, the spring moves down, I'm pushing it in the y. I'm pushing it in the x. If that's positive, the deflection, deflection goes up, pulls it to the right. Deflection goes down, pulls it to the left. And you start thinking, well, who in their right mind would have a boundary condition like that? So it doesn't make sense that there should even be anything like this. There should be just a number. Why would you have the Q 1, 2, and 2, 1?
Because it deflects as it getting pulled on it? Is it okay? If it goes down a little like that,
Yeah, it's kind of weird until you realize what happens if instead I put the spring straight up. Let's say I tilted it, and I had a spring that was off to the side. Now,
the thing is he allows me to put any number I want in it. So I don't have to make any physical reality out of this. Until you realize, wait a minute, if I have a spring that's say at 45 degrees attached to this silly thing, how would you implement that there? So in other words, this thing is saying, somehow I should be able to have some combination of these four numbers such that if I put a coordinate system like this, x prime and y prime, that the deflection in the x prime times the stiffness would be the force supplied in the x prime direction. Does that make sense? But you start looking at it, you start thinking, well, I don't have x prime, and I don't have y prime. I have x and y. So how do you relate those two? Until you realize, well, if I have a deflection in the x and a deflection in the y, equals to cosine of some angle, sine of some angle, minus sine of some angle, and cosine of some angle, that is the deflection in the x prime and deflection in the y prime. Okay, so let's look at this and see if it makes sense. I know that's the correct transformation, but I may have to change the sign. So a deflection of 1 in this direction. Okay, let's just go ahead and say it's 45 degrees because it really doesn't matter. So these are all 45 degrees. So as I move down a value of 1, what did I move? Okay, this is 1 and this is 0. Okay, the deflection of x is cosine of 45. Okay, that makes sense. Deflection of y, multiply that with that, is minus. So that seems legitimate. Now, if it deflect in this direction, then, okay, and didn't deflect in that one. This is the 0 and this is the 1. Multiply this comes out sine, so yes. And then this times that is cosine. Turns out that this transformation is correct for the picture I have. But then I've got this. And you're staring at this and you're thinking, oh my God, what is that? How can I do this? Until you realize, wait a minute, this is associated with if I just multiply k times that, I'm okay. That'll give me my force, right? So all I got to do is say, I deflected a certain amount here, but I did not deflect in the y. And then if that's the case, then I got a 0 here, so this transformation is cosine minus sine cosine. And then I've got a number here. And I got nothing here. And then I got this. So essentially I get cosine times that number, and it's minus sine times that number. Turns out you can map these q's back to this thing in an interesting way, so that you can tilt your spring any way you want. You can also tilt it in non-physical ways, which is what I would suggest, which doesn't make any common sense. So it allows you to do anything you want, whether it's physical or not. And that really monkeyed the works. I gave a 0, 0, 0, and a funny large number. But that doesn't have any physical significance. It's just that it solved the problem I told you. But you can have the spring such that if it deflects down, if it deflects like this, it doesn't produce any stress on it. If it deflects any direction in that component, it'll push it back in that way. And so, there are things you can do with that.
But you don't need to do them here, because in that problem statement, I just put a spring somewhere in there. Now the key is how do you implement that spring? What I would do is this. I would go in, let's get rid of this, and let me go back to the physical problem. What I'll do, can I move this? No, okay. Get rid of that. Oh yeah, I can move it. So I'd take my little region. Oh, I guess I can't. Okay. So here's what I would do if given that problem. Make a tiny little thing right there. So it's like a little wart there on it. And then I think you had one where, oops, you had another one over here that had a boundary condition. So here's your funny beam. You put the conditions there on it, or look at the boundary. Let's remove all those center sections. I'll go through the same process. I'll select them all. I'll make them so that they're free. There's no stress on them. I'll cantilever that left end. I'll make this one a spring, which, here, 1,000, 10,000, something like that. This one will be fixed. This one will be a load on top, minus 1E6 or something. Then if I go through the sequence here, I'll make it somewhat refined. Let me make sure I have my right, yes. Okay. And so what you should get, what you should have gotten, if I did that right, I think I may have done them in reverse order there. Which one? Oh, that's weird. I touched the wrong object there. I made that the boundary condition. I wanted that to be, that needs to be free. This needs to be fixed. So here, now you run it. You'll get kind of what we were talking about, what's kind of specified in that problem center. There's a little spring here, and this one's fixed, and then a load on the beam kind of causes it to do that. So the reason I put this little wart off the bottom is since you put your boundary conditions in a small set here. And so that's going to be a little bit of an issue there. So, and people are leaving, so either I've just gotten incredibly boring, which I'm sure I am, or it's time to go. So I'll just let this keep recording for a few minutes. So in case anybody had a question or something. So I'm going to hand write the rest of that stuff and give it all to you next time. Here, I'll stop the recording and I can tell you so.